As a continuation, let me work out some of the example problems. So in Fourier transform, so example 1, okay, find Fourier transform of function f of x, which is equal to 1 for mod x less than a and 0 for mod x greater than a. Okay, so we know that our Fourier transform f of s equal to 1 by root 2 pi integral minus infinity to infinity f of x e power I s x dx. Since our x ranges from a and it ranges, since it is a mod a function, it includes both positive and negative a. Okay, therefore for our case we have 1 by root 2 pi integral. Since it ranges from a, so it is from minus a to a, and f of x is 1 for within this limit e power I s x dx. Okay, for the other limit for which a greater than for which x greater than a, it's 0. Okay, so this is the only integral we have to evaluate. So if we integrate this one, we have 1 by root 2 pi, okay, e power I s x divided by is. Okay, so integral of e power I s x is e power I s x by is, and our limit is minus a to a. Okay, upon substitution of the limit, we have 1 by root 2 pi a 2 pi. So if we substitute the upper limit, we have e power I s x s a and by is minus e power minus I s a divided by is. Okay, so this is the upper limit minus lower limit. Okay, since the denominator is common, we have 1 by root 2 pi of is e power is a minus e power minus is a, and this form resembles somewhat like sine theta, since sine theta equal to e power I theta minus e power minus I theta by 2i. Okay, so the only thing we are missing is 2. Okay, so we are multiplying and divide by 2. So we have, so this part becomes, so let me take this 2 outside. We have 2 by root 2 pi, and instead of this, and we have a s here. Okay, and instead of this we can write sine sa. Okay, we can further simplify this. This this 2 can be written as root 2 into root 2 divided by root 2 into root pi, and we have sine sa by s. Okay, so this and this get cancelled, so finally we have root 2 by root pi, okay, sine sa divided by s. Okay, so this is the final answer. Let me work out another example. It's example 7 in the book, which reads, find the Fourier sine and cosine transform of f of x, which is defined as 1 for 0 less than x less than a, sorry, 1 for 0 less than x less than a, and 0 for x greater than a. Okay, so let me first find the Fourier sine transform. So Fourier sine transform, we know that Fourier sine transform is nothing but root of 2 by pi integral 0 to infinity f of x sine sx dx, right? So our f of x is 1 and the limit is from 0 to a. Therefore we have root 2 by pi integral 0 to a. Okay, so x is valid only for up to a. For above a it is 0. Okay, therefore integral 0 to a 1 into sine sx dx. Okay, actually what we have is plus integral a to infinity and 0 into sine sx dx. Okay, and this term becomes 0. Okay, because this is 0 because we know that for x greater than a our f of x is 0. Okay, therefore the integral we have to solve is integral 2 by pi integral 0 to a sine sx dx. Okay, so this is root 2 by pi of minus cos sx by s, and the limit is from 0 to a. Okay, so if we substitute the upper limit, we have root 2 by pi as common. So if we substitute the upper limit, we have minus cos sa divided by s minus minus of minus plus cos of 0 divided by s. Okay, so cos of 0 is 1, therefore we have root 2 by pi. So we can take this s as common, we have 1 minus cos sa. So this is the answer. So next we have to find this cosine transform. Okay, so our cosine transform is Fourier cosine transform equals to root 2 by pi integral 0 to infinity f of x cos sx dx, right? And similarly we have root 2 by pi integral 0 to a, and other limit becomes 0, cos sx dx. Okay, which is nothing but root 2 by pi, and upon integration we have sine sx by s, and the limit is from 0 to a. Okay, so if we substitute the upper limit, we have sine sa divided by s minus sine 0 by s. Okay, and this sine 0 is 0, therefore we have root 2 by pi sine sa by s. Okay, so this is the final answer. Let me work out the next example, which is example 2 in the book. So it is example 2, which reads that find the Fourier transform of f of x, which is defined as 1 minus x square for mod x less than equal to 1 and 0 for mod x greater than 1. Okay, so to tackle this, you can start with the Fourier transform formula. We know that f of s equal to 1 by root 2 pi integral minus infinity to infinity f of x e power I s x dx, right? So this is the formula. And our limit, since it is a mod x, our x runs from minus is both minus and plus value, and our x is defined between the limit at the maximum of from -1 to 1. For x above 1, our f of x is 0. Therefore we have root 1 by 2 pi integral -1 to 1, and instead of f of x we can put our function 1 minus x square e power I s x dx, right? So this integral is of the form integral u dv. Therefore we can split our u and dv based on our late rule. So according to that rule we have to choose u such that it obeys that late law. Okay, that is, we can choose u as log, inverse, algebraic, exponential, trigonometric, and lastly we can choose exponential. Okay, so accordingly we have here both exponential and algebraic form. So this is the two choice. Okay, choice of u. Okay, so we are choosing our algebraic form. Okay, because this is in the priority list, we have exponential in the last. Okay, so we should not choose this as our u. Okay, so this is our u and this is our dv. This entire thing is dv. Okay, therefore, so upon substituting it on the integral u dv form, we have root 1 by 2 pi. This is our coefficient. We have u dv. dv is this one, uv. Okay, so this, if we find dv, it is, we have to integrate this. So we have e power isx divided by is. Okay, so this is our v, minus integral so we have integral -1 to 1, and it's v du. Okay, so v is this one, e power isx divided by is v du. If we differentiate this function, we have minus 2x, okay, dx. Okay, and this runs from -1 to 1. Okay, we can simplify this later. So if we notice, we again encounter another integral of this above form. Okay, so again we have to separate u and dv. So this part is u and the dv part is dx and this one. Okay, therefore we have root 1 by 2 pi 1 minus x square e power isx divided by is. Okay, we can simplify this later, minus integral, and for this thing we have, so it's uv. Therefore our u is this one, so minus, we have a minus outside, minus 2x u v. Okay, so we have to find it is in dv form. So if we integrate this, we will have e power isx divided by is the whole square. Okay, so this is dv, right? So this green color is dv. So we want to find v. For that we have to integrate integral -1 integral e power isx divided by is into dx. So For that we will end up with this one. Okay, and our integral v du is minus, so we have a minus integral v du. Okay, integral minus 1 to 1 v. What is v? Our v is e power isx divided by is the whole square. This is our v, and our du, for du is minus 2, right? Dx. Okay, this one runs from minus 1 to 1. Okay, so let's multiply this minus inside and integrate this one. Therefore we will have 1 by root 2 pi 1 minus x square e power isx divided by is. Minus of minus 2 is plus 2x into, and we have a limit minus 1 to 1 here. Okay, and we have e power isx divided by is the whole square, and which runs from minus 1 to 1, and this minus and this minus becomes positive, and we have a minus 2 here. We can take that outside, and if we integrate integral minus 1 to 1 e power is x dx, we will end up with e power isx divided by is whole cube, right? This runs from minus 1 to 1. Okay, finally we have cleared all the integrals, so we have to substitute the limits. Okay, so let's try to substitute the limits. 1 by 2 pi. So for the first thing we have, so if we substitute the upper limit, it will become 0, and for lower limit also it will become 0, so the full term becomes 0. Okay, if we substitute the upper limit, this 1 square is 1, therefore 1 minus 1 is 0, therefore the whole term is 0. And if we substitute the lower limit also, minus 1 the whole square is 1, and 1 minus 1 is 0. Okay, so for all values of the limit, this term is 0. So we next end up with this one. So if we substitute the upper limit, we have 2 into e power is, instead of x we are putting 1, divided by is the whole square, right? Upper limit minus lower limit. Okay, minus of minus is plus, 2 times, instead of x we have to put minus 1, and e power minus is, right, divided by is the whole square. Okay, so this term is finished. Next we move on to this one. So if we substitute the upper limit, we have minus 2 e power is divided by is the whole cube. Okay, and minus the lower limit, minus of this minus becomes plus, and if we substitute the lower limit, we have 2 times e power minus is divided by is the whole cube. Okay, let's try to simplify this term even further. So we have, so this I square becomes minus 1, therefore we have minus 2 e power is divided by s square. Okay, and this one is plus 2. Okay, and if we substitute this one, this again becomes minus 2 e power minus is divided by s square, and for this we have we have a plus 2 e power is divided by is cube. Okay, so we left with a minus, sorry, we left with an I. Okay, then this I square here becomes minus 1, and minus of minus is plus, so we have this one, and here we have minus 2 e power minus is divided by is cube. Okay, and then further simplification, we can take minus 2 by a square as common term. So therefore, if we take minus 2 by a square, we have e power is minus e power minus is. Okay, in this one, and we can take plus 2 by is cube. Okay, and we end up with e power is minus e power minus is. Okay, sorry, here we have a plus. Okay, can multiply and divide by 2. Here also we can multiply and divide by 2. Okay, and just multiplying and divide by 2, therefore we can write this as, this is nothing but, and we can take this I inside. Okay, and this part, this is nothing but cos theta, sorry, cos yes. Okay, and this part is our sine s. Okay, this is sine s. Okay, so we have 1 by 2 pi minus 2 times x square into 2 times cos s. Okay, plus 2 by s cube into 2 times sin s. Okay, and this is equal to root of 1 by 2 pi minus 2. So we can take this, here we have a 4, and here also we have a 4, and we can take s cube outside, therefore we can have 4 by s cube of, so since here we have only a square, we have to multiply and divide, therefore we have minus s cos s, right, plus sin s. Okay, so this is the final simplification. Let me work out the another example, and it's example 3 in the book. States that find the Fourier sine and Fourier cosine transform of f of x, which is equal to e power minus ax. Okay, so this is our f of x. So let's start with our known formula. We know that Fourier sine transform equals to root 2 by pi integral 0 to infinity f of x sine sx dx. Okay, so if we substitute the our f of x, we have root 2 by pi integral 0 to infinity e power minus ax sine sx dx. Okay, so and this is an standard integral, and we have root 2 by pi, and the value of this integral is root 2 by pi, and the value of the integral is e power minus ax divided by a square plus s square minus a sine sx minus s cos sx. And it's between the limit 0 to infinity. Okay, upon substitution of the limits we have, so for the upper limit this e power minus infinity is 0. Okay, so we left with only the lower limit, and for the lower limit we have root 2 by pi and 0 for upper limit minus the lower limit is e power 0 divided by a square plus s square and minus a sine 0, sorry it's not theta, it's 0 minus s cos 0, right? And this is 0, so we have root 2 by pi and e power 0 is 1, therefore we have minus 1 divided by a square plus s square of minus cos 0 is 1, it's 1, therefore we have minus s. Okay, therefore it is root 2 by pi s divided by a square plus s square. Okay, so this is the Fourier sine transform. Similarly, we have to find the Fourier cosine transform. Let me write the Fourier cosine transform formula. So our Fourier cosine transform is equal to root 2 by pi integral 0 to infinity f of x cos sx dx. Okay, and our f of x is e power minus ax, therefore we have root 2 by pi integral 0 to infinity e power minus ax cos sx dx. Okay, again this is a standard formula, standard integral, therefore we have root 2 by pi of e power minus ax divided by a square plus s square of minus a cos sx, okay, plus s sine sx. Okay, and the limit is from 0 to infinity. Upon substitution of the limits, for upper limit it is e power minus infinity, which is 0, and 0 into everything is 0, so only as mentioned before, only the lower limit exists. Okay, therefore we have root 2 by pi, so this is for the upper limit, minus for lower limit we have e power 0 divided by a square plus s square of minus a cos 0, sorry it's cos 0 plus s sine 0, right, and this sine 0 is 0 and cos 0 is 1 and e power 0 is 1, therefore we have root 2 by pi of minus 1 divided by a square plus s square into minus a, right, Therefore the Fourier cosine transform of e power minus ax is root 2 by pi a divided by a square plus s square. Okay, so this is our final answer. Let me move on to the next example. It's example 5 in the book. So I am writing example 5, working out example 5, and it reads find the Fourier cosine transform of, okay, so find the Fourier cosine transform of e power minus 2x plus 4 e power minus 3x. Okay, so let's start with the formula. So the Fourier cosine transform of f of x is root 2 by pi integral 0 to infinity f of x cos sx dx, right? And our f of x is this one. So this is our f of x. Okay, therefore we have root 2 by pi. Let me write from here. Okay, so we have root 2 by pi integral 0 to infinity. Instead of f of x we have to put this one. Therefore e power minus 2x plus 4 e power minus 3x cos sx dx. Okay, again we have to use the previous formula. When instead of a we have 2 here. Okay, therefore it is root 2 by pi and integral 0 to infinity e power minus 2x cos sx plus 4 times integral 0 to infinity e power minus 3x cos sx dx. Okay, since we find this integral, we know that integral 0 to infinity e power minus ax cos sx equals to a divided by a square plus s square. Okay, so this is a well-known fact, so we can use this one for evaluating this integral. Therefore we have root 2 by pi, and instead of this we have, for a we have 2 here, therefore it is 2 times 2 square plus s square, right, plus 4 times this 4. Okay, and instead of this we have this integral, and for this our a is 3, therefore 3 times 3 square plus s square. Okay, so we can take 2 outside as a common factor. Therefore we have 2 root 2 by pi, and it's 1 by 4 plus s square plus, since we take 2 outside, so we are left with 2, and 2 into 3 is 6, 6 divided by 9 plus s square. Okay, so this is our final answer. So let me work out the next problem. So it's example 4 in the book, and it reads find Fourier sine transform of f of x equals to 1 by x. Okay, so this they asked to find the Fourier sine transform. So we know that the Fourier sine transform of f of x equal to root 2 by pi integral 0 to infinity f of x sine sx dx, right? And if we substitute our f of x, we have integral 0 to infinity sine sx by x dx. Okay, so we have a standard integral for sine theta by theta, but we have sine x sx divided by x. Okay, for that we have to do a simple transformation to make this this function to become sine theta by theta. Okay, for that let's make a transformation, which is by putting Sx equals to theta, we have Ex equal to theta by x, right? Sorry, theta by s, and dx equal to d theta, and when x tends to 0, theta tends to 0, and similarly when x tends to infinity, theta tends to infinity. Okay, since they are directly related, so s is a constant, so this is the thing, so there is no change in limit, so we can directly substitute this in the above equation. We have root 2 by pi, and our integral is from 0 to infinity, and our sine sx become sine theta, and our x equal to theta by s, so I will take this s to the numerator, and our dx equals to d theta. Dx equal to d theta by s. Okay, therefore we have d theta by s. Okay, this s and s gets cancelled out, so we have root 2 by pi, and this integral, this is a standard integral, so it's from 0 to infinity sine theta by theta d theta, and this is equal to root 2 by pi, and the value of this integral is pi by 2 . So let me bring this here so you can understand it in a better way. Okay, this is equals to pi by 2. Okay, this integral value is equals to pi by 2. So on further simplification, we can write this as root 2 divided by root pi, and this pi as root pi into root pi, and this 2 as root 2 into root 2. Therefore they get cancelled, and we have root pi by root 2 or root of pi by 2. Okay, so this is our final answer. So the next example is example 6. Okay, example 6, and it is find Fourier sine transform of f of x is equals to e power minus ax divided by x. Okay, so that we can find it by using our formula. We know that Fourier sine transform of s equal to root 2 by pi integral 0 to infinity f of x sine sx dx, right? And if we substitute our f of x, we have root 2 by pi integral 0 to infinity e power minus ax divided by x into sine sx dx. Okay, so to proceed further, we have to differentiate this with respect to, so let me number this as equation 1. So differentiating equation 1 with respect to ds on both sides. Okay, we have d by ds of f of s equals to root 2 by pi integral 0 to infinity. Since we are differentiating with respect to s, we can take this differential operator inside, because our integral is with respect to dx, so it won't affect anything. Therefore we can write, since this is independent of x, we can take this as a outside, and we can write as d by ds of sine sx. Okay, we can put this dx this side. Okay, and if we differentiate this one, we have cos sx into s, because we are into x. Okay, since we are differentiating with respect to s. Okay, let me write this one. So we have integral 0 to infinity, and this term is e power minus ax by x dx into, and this differentiation is cos sx into x. Okay, since we are differentiating with respect to s. Okay, and this x and this get cancelled, so we end up with root 2 by pi integral 0 to infinity e power minus ax cos sx dx. Okay, and this is our standard integral. We already worked out this one, and the value of this integral is nothing but root 2 by pi of a divided by s square plus e square, right? And this side we still have this d by ds of f sine of s. Okay, so we have to get rid of this ds, so we are integrating with respect to ds s. Okay, so upon integrating both sides with respect to s, we have integral of d by ds of f of s equals to root 2 by pi integral 0 to integral a divided by s square plus a square into ds. Okay, so this comes to that side. Okay, and this integral and this differentiation is get cancelled out, so we end up with f Fourier sine transform equals to root of 2 by pi, and this is again a standard integral, and this value of this integral is tan inverse of s by a. Okay, and since this integral is an indefinite integral, we have a constant of integration. Okay, so we have to find this constant of integration. For that, we have to find the value of our Fourier sine transform at the origin. Okay, so therefore at s equal to 0, Fourier sine transform of 0 equals to root 2 by pi tan inverse of 0. Okay, plus c. Okay, and this is nothing but 0, therefore our c is equals to 0. Therefore our c equals to 0. So if we substitute this, we have f sine Fourier sine transform of e power minus ax divided by x equals to root 2 by pi tan inverse of s by a. Okay, so this is our final form, and this is nothing but Fourier sine transform of e power minus ax divided by x. Okay, this is our given problem. So the next example is example 8 in the book, and it states that find the Fourier transform of Dirac delta function. Okay, so Dirac delta function. Okay, so it is somewhat an important problem, Dirac delta function, and it is defined as d of x minus a. Okay, so for that we have to know what is this Dirac delta function, and this Dirac delta function x minus a is defined as in the limit h tends to 0 f of x. Okay, and this f of x equals to one by h for a less than x less than a plus h, and 0 for all other values. Okay, for 0 for x less than a, and 0 for x greater than a plus h. Okay, so we have to find the Fourier transform for this one. Therefore, the Fourier transform from, we know that the Fourier transform of f of x equal to 1 by 2 pi root of 1 by 2 pi integral minus infinity to infinity f of x e power isx dx, right? Therefore, if we substitute our f of x, we have root 1 by 2 pi, and we have the limit h tends to 0 integral, and our x exists only in the range a to a plus h. For all other values, our f of x is 0. Okay, so and for in this range the value of f of x is 1 by h. Okay, therefore 1 by h, and the limit is from a to a plus h. Okay, a to a plus h e power isx dx. Okay, since the integration is with respect to x, we can take this h outside. Therefore, we have 1 by root of 1 by 2 pi limit h tends to 0 1 by h, and the integral of e power isx dx is nothing but e power isx divided by is. Okay, and the limit comes from a to a plus h. Okay, and upon substitution of the limit, we have root of 1 by 2 pi limit h tends to 0 1 by h, and for upper limit we have e power is a plus h divided by is, and for lower limit we have e power is a divided by is. Okay, so we can separate this one, and we can take e power ias as common. Therefore, we have root 1 by 2 pi limit h tends to 0 1 by h into e power isa. Okay, and we have e power is h divided minus 1 divided by is, and we can take this h inside. Therefore, we have h. Okay, here. Okay, and this is nothing but e power theta minus 1 divided by theta. Okay, so this looks similar to e power theta. Okay, so this one looks similar to e power theta minus 1 divided by theta. Okay, and in the limit theta tends to 0, this value is nothing but 1. Okay, so we can take this e power I SA outside of the limit, and we have root of 1 by 2 pi e power I SA into the limit h tends to 0 e power ISH minus 1 divided by ISH, and this is nothing but 1. Okay, therefore we have root of 1 by 2 pi into e power ISK. Okay, so that's our result. Okay, you may ask how this is possible, and for that I am writing a proof. So we know that e power theta equals to 1 plus theta square by 2 factorial plus theta cube by 3 factorial plus etc. Okay, I am taking this one this side, therefore we have e power theta minus 1 equal to theta plus theta square by 2 factorial plus theta cube by 3 factorial plus etc. Okay, so now I am dividing the whole equation by theta, therefore e power theta minus 1 divided by theta equal to 1 plus theta by 2 factorial plus theta square by 3 factorial plus theta cube by 4 factorial plus etc. Okay, so in the limit of low value of theta, that is in the limit theta tends to 0, e power theta minus 1 divided by theta equals to, so if we substitute theta equals to 0, this all terms becomes reduces to 0. Okay, therefore we left with 1. Okay, that's the proof for why our in the limit theta tends to 0, e power theta minus 1 divided by theta equal to 1. Okay, that's the proof. So let's work out another example. It's example 9, and it says show that Fourier sine transform of x f of x equals to minus d by ds of Fourier cosine transform of s and Fourier cosine transform of s x f of x equals to d by ds of Fourier sine transform of s. Okay, so we have to prove this one, and using this results from this proof we have to find the Fourier cosine transform and Fourier sine transform of x e power minus ax. Okay, so let's try to find the Fourier sine transform of this function. Okay, so we know that Fourier cosine transform equal to root 2 by pi integral 0 to infinity f of x cos sx dx. Okay, and this is nothing but Fourier cosine transform of f of x. Okay, so next we have to find, so what we are going to do is we are going to differentiate this with respect to ds. Okay, so upon differentiating on both sides with respect to ds, so with respect to s, we have d by ds of s equals to root 2 by pi integral 0 to infinity. Since the integral is with respect to x, we can take this ds, this differentiation inside, so therefore we have d by dx into d by ds of cos sx. Okay, and this is nothing but root 2 by pi integral 0 to infinity f of x dx into, and this is minus sine sx into x. Okay, and therefore we have root 2 by pi integral 0 to infinity, and we have a minus outside, and x f of x into sine sx dx. Okay, and this is nothing but our minus of Fourier sine transform of x f of x, right? So we proved that d by ds of Fourier cosine transform of s equals to this one. Okay, next we have to prove the Fourier cosine transform of, the differentiation of Fourier sine transform of f of s equals to that one. Okay, this the next thing is we have to prove this one, and we can take this minus sign here, and then that's the proof. Okay, so for the next proof I have to take the Fourier sine transform. Okay, so for next proof, okay, the next proof, so for that we have to take Fourier sine transform of s equals to root 2 by pi integral 0 to infinity f of x sine sx dx. Okay, here also I am going to differentiate with respect to ds on both sides. Therefore we have d by ds of f of s equal to root 2 by pi, and since the integral is with respect to x, we can take this ds inside. Therefore we have f of x dx into d by ds of sine sx. Okay, and the differentiation of this function gives root 2 by pi integral 0 to infinity f of x dx into cos sx into x. Okay, and this is nothing but root 2 by pi integral 0 to infinity x f of x cos sx dx. Okay, and this is nothing but our Fourier cosine transform of x f of x, and this side we have the differentiation of Fourier sine transform with respect to s. Okay, so we have proved both of this one. Next we have to use this proof to find the Fourier sine and cosine transform of our f of x. Okay, this is our f of x, and our f of x is x e power minus ax. Okay, for that let's start with the known formula. We know that we have already worked this one. So the Fourier sine transform of e power minus ax, okay, is nothing but es divided by a square plus a square. Okay, we have already worked this one. And the Fourier cosine transform of e power minus ax equals to a divided by root of a square plus x s square. Okay, so what's the Fourier cosine transform of x into e power minus ax? Okay, so this is nothing but of this form. Okay, this one, x into this f of x. Okay, so here this is our f of x in this case. So from this proof we can write the Fourier cosine transform of, okay, let me write this. So from this we can write the Fourier cosine transform of x into some f of x is nothing but, and this side we have, and this is nothing but our, this entire thing is nothing but Fourier sine transform of f of x. Okay, therefore we have it's nothing but d by ds of d by ds of Fourier sine transform of our f of x, and our f of x is nothing but e power minus ax. Okay, and we know that this Fourier sine transform of this is nothing but this one. Okay, so we have to substitute this here. Therefore we have d by ds of s divided by a square plus a square. Okay, for this we have to use our u by v formula. So we have to use u by v formula. So, and it states that, and our u by v equals to v du here. So we have to use u by v formula. U by v equal to v du minus u dv divided by v square. Okay, therefore if we use this one, we have, and our v square is a square plus a square, the whole square, and our v a square plus a square, and the du is ds, d by ds is 1, and we have minus, and u is this s, and dv is, we have to differentiate this one, therefore we have 2s. Okay, so the final expression is a square plus a square, the whole square. Here we have a square plus s square minus 2s square, right? Therefore we have a square plus, a square minus s square, and here we have a square plus s square, the whole square, and this can be written as, so this is the final one. So what we start here is the Fourier cosine transform of Fourier cosine transform of x e power minus ax equals to this one. Okay, similarly we have to find the Fourier sine transform of, so Fourier sine transform of x into e power minus ax, and we know that the Fourier sine transform of this Fourier sine transform is nothing but minus d by ds of Fourier cosine transform of e power minus ax. Okay, and we also know that the Fourier cosine transform of e power minus ax is nothing but a divided by a square plus s square. Therefore we have d by ds of a divided by a square plus s square, and upon differentiation we have to use our u by v method. Therefore we have so if we use our u by v formula, then we have this is our minus sign of this one. Therefore this is a square plus s square the whole square, and v du v is our a square plus s square into du, and du is dA by ds, which is 0, minus u dv. Okay, so our u is a and dv is d by ds of a square plus s square, which is 2s. Okay, therefore this term becomes 0. Therefore we have minus of minus is plus, so we have 2as divided by a square plus s square the whole square. So I made a small mistake. Here we have a factor of root 2 by pi, and here also we have a factor of root 2 by pi. Okay, so if you recall, this Fourier cosine transform is this one. Okay, we left with this root there. Okay, so we have to add that one here. So we have an extra root 2 by pi, and here also we have an extra root 2 by pi. Okay, and this is our Fourier sine transform of x e power minus ax. So let's work out the last example, and it's example 10 in our book. So it says find Fourier cosine transform of e power minus a square x square, and hence find evaluate or find the Fourier cosine transform of Fourier cosine transform of Fourier, not Fourier cosine transform, Fourier sine transform. Okay, and hence find the Fourier sine transform of x into e power minus a square x square. Okay, so let's try to solve this one. So first we have to find the Fourier cosine transform of this one. So we know that Fourier cosine transform equal to root 2 by pi integral 0 to infinity f of x cos sx dx, and our f of x is this one. Therefore we have root 2 by pi integral 0 to infinity, and instead of f of x we have to put e power minus a square x square into cos sx dx. Okay, so instead of let me rewrite this as this whole equation as real part. Okay, so this is real part of root 2 by pi integral 0 to infinity e power minus a square x square into cos sx plus I sine. Let me move this one here so I can write it easily. And I sine sx dx. Okay, so if we take the real part, it's just this root 2 pi integral 0 to infinity e power minus as cos. Okay, we have to remove this sign, then we get back this integral. Okay, I am just writing this integral in this form. Okay, and let me carry out this one. So real part of root 2 by pi integral 0 to infinity e power minus a square x square into e power, this is nothing but e power I sx dx, right? Okay. And there is a standard formula for the integral, so this is a standard integral, this is a standard integral, the integral formula. Okay, so any integral 0 to infinity e power minus ax square into e power bx dx equals to 1 by 2 root of pi by a into e power b square by 4a. Okay, so this is a standard integral, so we have to use this here. Therefore, if we use this standard integral here, and instead of b we have is. Okay, therefore let's continue. So the real part of root 2 by pi, so this integral can be written as 1 by 2 root pi by a, because a and a matches, and instead of b we have is, therefore e power is the whole square divided by 4e, right? Also here we have a, whereas here we have a square, therefore in the formula we have to put, instead of a we have to put a square. Okay, here all and here, right? So this is just a constant, so it can be a square of something. Okay, so this is real part of root 2 by pi into 1 by 2 root pi by a square into e power, this can be written as so this is minus, right? We have a minus, since it's I square we have minus s square divided by 4a square. So this can be even further reduced, so we just keep this real part thing for our memory. So we have the real part, and this is root 2, and we have root pi. Okay, I am just writing root 2 by pi as root 2 into 1 by 2, instead of 2 let me write as root 2 into root 2, and we have a pi here, root pi here, and we have a root a square, and we have e power minus s square divided by 4a square. Okay, so we can cut this one, this one, and therefore we have real part of, and here it is root 2 and this is a, therefore we have real part of 1 by root 2 into a e power minus s square divided by 4a square. Okay, and if we see there is no imaginary part, so the real part of this is equal to this itself, therefore we can write this as 1 by root 2a, okay, e power minus a square divided by 4a square. Okay, and in this side we have what we have here, and this side we have the Fourier cosine transform of, so here we have Fourier cosine transform of e power minus a square x square. Okay, so this is the okay. Next, so with this we have finished the first part, and with this result we have to find the next thing, which is find the Fourier cosine transform of find the Fourier sine transform of x into e power minus a square x square, right? So they asked to find this one. So we know that already, like Fourier sine transform of x into f of x is nothing but minus d by ds of Fourier cosine transform of f of x, right? We have already proved this one. So here if we consider, instead of f of x we have e power minus ax square. Okay, so we can write this Fourier sine transform of x into e power minus a square x square equals to minus d by ds of, and instead of f of x we have to find the Fourier cosine transform of e power minus a square x square. So this is what we have already done here, so we can substitute this here. Okay, so it is nothing but minus d by ds of 1 by root 2a into e power minus s square divided by 4a square. Okay, so if we differentiate this, and we have a minus here, and if we differentiate this we have, so these are constant things, we can take this outside, so it is minus 1 by root 2a, and if we differentiate this we have e power minus s square by 4a square, okay, into 2s times 2s divided by this minus 2s. Okay, we have a minus 2s because divided by 4a square, right? So this minus and this minus get cancelled, and this root 2 and this can be written as, so this 2 is written as root 2 into root 2 into s divided by, here we have a root 2 and a, and from this we have 4a square, right, and we have another exponential of minus a square by 4a square. Okay, and we can simplify this one, and we end up with s divided by 4a cube into e power minus a square divided by 4a square. sorry, we have a root 2 here. Okay, so there is another root 2. If we need, we can further simplify this by making this 4 as root 2 s divided by 2 into 2 a cube of e power minus s square divided by 4a square, and this 2 can be written as root 2 into root 2, and we can further simplify this, and we have s divided by 2 root 2. Okay, let me write somewhere here. Okay. S divided by 2 root 2 a cube e power minus s square divided by 4a square. Okay, so this is the final answer, and this side we have the Fourier sine transform of x into e power minus a square x square. Okay, so this is the final answer.